Homework 38, 566. We are in chapter 9 now, jumping around. We will continue jumping around. We're going to do a couple sections from chapter 9 and then probably jump around to a bunch of other things. Section 9.1, numbers 1 through 17, odd. Yes, that's it. 1 through 17, odd. That's 9 questions, I think. So you're welcome. So, a couple things to review. And so we got a couple of things that are going to help us out today. First off, let's start off thinking about this. Y equals f of x. Okay, I could write y of x if I want, but we have some function. Inputs are x's, outputs are y's, so this makes us think of the regular old x, y axes and stuff like that. Now, we've talked about the Leibniz notation before. That's dy dx, which simply just means the derivative of f with respect to x. And we usually use this notation. Today, it will be in our benefit to write stuff this way. You'll see why. But there's just a couple other things I want to say from here, right? Remember that we could think about this here as what we did here is we took a derivative. In other words, we used this operator, dx, right? Which means take the derivative of this thing with respect to x, so that x is your input variable. Which means take the derivative of this thing, which is f of x, with respect to x, which gives us that right there. And we just write shorthand dy dx for that. And this isn't. You could also, if you wanted, you could call this df dx. That's perfectly fine. Sometimes we'll do that, whatever. But this means this, right? And think about what that means, right? Because the derivative is the change in y over the change in x, right? So your y at x plus h minus y at x all over x plus h minus x. In other words, delta x, right? How much does y change right there? That's delta y. How much does x change right there? That's delta x. And then when we take a limit, we write dy dx, right? So that now you take the limit as, I guess, delta x goes to 0, whatever, what you get is dy dx. This is the same kind of thing when we set up a Riemann sum, right? And we have delta x in there. And then when we take the limit of the sum, we write dx instead of delta x. Okay, so a couple things about this. Now, we could continue to take derivatives of this. And if we take the next derivative, we say take the next derivative with respect to x of this thing. And this is, all this is notation here. I'm not introducing anything new. I'm just saying take the derivative of this thing. Well, it's already a derivative. And so over here in this notation, we would just write f double prime, or the second derivative of f. Over here, though, we have a slightly different way of writing it. And what we do is, this means the second derivative. And the way we write that is we write d squared y dx squared. And it doesn't mean that you're squaring x or that you're squaring d or anything like that. It just means that that's what you've done. So if you have the fourth derivative, you would write that as d4y dx to the fourth. That's all it means. Okay? We're going to see that. I'm going to do that today, and I don't want that to be weird when you see it. There's a couple other things to say about this. One really, really nice thing about this notation is when it comes to the chain rule. Is that, and especially if you go on to take multivariable calculus, where the functions that you're dealing with have more than one input, like you have a function of x and y, then you're pretty much exclusively going to be using Leibniz to figure out how you do that. Because, as we'll see in a second, this is really useful for the chain rule. So the chain rule for this says, okay, right now, what we do is when we take the derivative with respect to x of a function inside of another function, right? What we do is we treat g as the variable itself, right? We take the derivative of f with respect to g, and then we multiply by the derivative of g. And the way that looks is you have f prime g of x times g prime of x. In Leibniz notation, what you're doing is you're saying that the derivative here, the derivative with respect to x of a function y, which is a function of x and g, you say first take the derivative of the thing with respect to g, then you take the derivative of g with respect to x, which is what this is, right? That's all that means. And just to drive the point home, here's an example. Let's say that y equals 1 over g. So in other words, y is a function of g. Yeah? Now I take the derivative of it. What's dy dg? No, the derivative, not the antiderivative. Negative g to the negative 2, right? Like that. Times the derivative of g, but if it's just g, then we stop there. But now we're going to pretend that g is a function of x. So at the very beginning, what we had was something like this. 1 over, I don't know, how about 2x plus 1? If I told you take the derivative of that, you'd say, okay, I'm going to pretend that this is just 1 over something. And you'd get this right here. 2x plus 1 squared. Then you'd multiply by the derivative of that stuff, which is what? 2. And so the thing that we'd be missing here, you would say, okay, take the derivative of y with respect to this thing as a variable, like that thing as g, and then you multiply by the derivative of g, with respect to x. So this is really nice with the chain rule, and then you could see that those dg's cancel, and what you have is the derivative of y with respect to x. And you might ask, and this is something that's, I'm just going to do it in a minute, and I'm going to say, we're going to have a bunch of d's, like it's going to look like this, dh, df, df, dx, and then we're going to have like a dx, df, and I'm just going to say, look, these cancel. The dx's are going, and the df's are gone. And you might, you might not believe that. I didn't believe it, and I had to work it out. And it's true, it does work. And I would suggest if that really bothers you, actually try to work it out. But it should make some sense, because remember at the beginning, what did I say that this was anyway? dy dx was the change in y over the change in x, and then we just take a limit of it, right? And so if you have a bunch of expressions like dy dg, and then you're multiplying that by, I don't know, dg dx, what this is the limit as they do what they do, as they all better go to 0. Right? I mean, that's the idea, because you have the change in height over the change in width. They're all going to 0 as you're taking your limit. But what you have is a delta y. Over here you have a delta g. Up here you have the same delta g, right? And a delta x. And if you really wanted to be explicit, you could say, here's the limit of my y1 minus y0. Over here's my g1 minus g0. Down here you have your still same g1 minus g0. And down here you have your x1 minus x0. And so these guys do indeed cancel out. Except when they don't, but then you're dealing with functions that are crazy, and we're not dealing with those kinds of functions. The functions we deal with have this property. So it's just something to note, okay? Because I'm going to do this in a second. Could you guys please try to keep it down? I'm going to do some stuff with this in a minute. I'm just going to cancel some stuff. It does work. But that's not really where we're going with this. One last thing about this Leibniz notation. So I already said, if we have some function just f of x, then dy dx is just f prime of x. And I said you could take second derivative of it with respect to x and you'd get d squared y dx squared. What if we wanted to take the derivative with respect to y? And this is where it's weird. But let's think about implicit functions here, right? Like if we had x squared plus y squared equals 1. We could take the derivative of both sides of this thing, right? And if we're taking the derivative with respect to x, dx over here, that goes to 0. Then that's just 2x, no problem there. But now we treat y as a function of x and da-da-da-da-da, and so the 2y comes down, but then we multiply by the derivative. Or we could do it in Leibniz notation, dy dx, like that, right? So we've dealt with that before. Here, this function itself might be a function of y. We don't know, right? Like, this expression may have y's in it. We don't know whether it does or not, right? But we could pretend that it does. The same way we pretend, there's no x in there, but we could pretend that there is, that this thing is somehow a function of x. It's kind of the same thing here. This is just some function. We could call it g for all we care, g. And what are its inputs? Well, it might be y, it might be x, it might be t, right? Maybe y is a function of t, and x is also a function of t. We don't know. But we could just say in general, maybe there's a y in there, maybe there's an x in there, it might be both. And if that's the case, and you then want to take the derivative with respect to y, we need to use the chain rule again. And so when we do that, and I'll just do it like, forget about this for right now, just saying you have some function. It's a derivative of something with some variable. And now you want to take its derivative with respect to the top variable. What we have to do is, again, the chain rule. We're going to pretend that y is a function of x because it tells us that it is. Right? That's what that means. The inputs are x's, the outputs are y's. And so we have to say, okay, chain rule says, take the derivative of this stuff, then multiply by the derivative of that stuff. Right? So we would say d squared y dx squared. In other words, the second derivative. But then you multiply by dx dy. Is that bending your brain? It does work. It is what you have to do because that's just the chain rule. Right? And maybe we could see this a little bit better if instead of thinking about y, we think about this as a g of some stuff. There's an x in there, there's some other stuff in there. And then if I take the derivative with respect to y, we use the chain rule, and whatever's in here, maybe we'll call it u. The chain rule would say, okay, take the derivative of this with respect to u, then multiply by the derivative of u. That's what we're doing right here. But it's the derivative of u with respect to y, dy. And here you're taking the derivative of g with respect to u. Right? So this is dg du, du dy, dy dx, dx dy. It just so happens that the second derivative works out that way. Yeah. It's a little funky, and again, this was something I didn't quite believe. I had to work it out from first principles to really make myself believe this. And you could do that. Like you could, again, just rewrite this as a function, write what it would be with respect to y. Funky stuff happens, but it does work out to be this right here.
Doesn't that just cancel?
Right now, that does not cancel. Because this dx squared is not just dx, then squared. And when you work that out, you'll see it's not that simple. But actually, you might be able to write it that way. It might actually work that way. But the thing, like I said earlier, we're going to have something else that will be better to cancel with to make our lives easier. And so we will want to write it this way. But this is just by the by. Right? This is I want to get this up on the board now so that when we actually do the thing that we're doing, I could just do it without stopping and saying all of this stuff. Okay? So these are, like, we could have done all this when we were doing the chain rule and implicit differentiation. We've actually done it all before, it's just we haven't done it in Leibniz notation. So, guys, please. So, this is stuff we've done before, just in Leibniz notation. Now, here's some stuff that you may or may not need for this homework. I haven't looked carefully at all of the problems, but something like this might show up. Does anybody remember what this is? It's cosh, the hyperbolic cosine. Does anybody remember what it is? I'll give you a hint. It's something over 2.
Sine x, sine of x over 2?
No.
Oh.
Like, 2.
That's what it is.
Okay.
That's the definition of cosh, or the hyperbolic cosine. You might say, what does that have to do with cosine? Well, if you recall, e to the ix is cosine x plus I sine x. E to the minus ix is cosine x plus I sine negative x. Pull the negative out and you get a minus. Add all these guys together and you get e to the ix plus e to the minus ix equals, those guys cancel and you get 2 cosine. Divide through by 2 and you get this. So then cosh is very similar to this guy. It's just without the i's. Take out the i's and you have cosh. Okay? Sinh, we get the same way. We say sinh is e to the x minus e to the minus x all over 2, which if we subtracted these guys here, so instead of adding, I'm going to subtract. The cosines are gone. We have I sine x minus I sine x, 2i sine x. Divide through by the 2i, and so then it's off by an i and the i's. Right, so this is, now, but this isn't the only reason why they're called the hyperbolic trig functions. And why hyperbolic, of all the things? Why? What does that have to do with a hyperbola? Well, let's just recall here, I'm going to use a big X, let's say x of t, if that's cosine t, and big Y of t is sine of t, then x squared plus y squared is equal to cosine squared plus sine squared, which is 1. And what object is this?
It's a circle.
It's a circle. So we could think of the trig functions as the circle functions. Now let's see what happens if we attempt the same thing with cosh and sinh. Here's my claim, is that cosh squared x minus sinh squared x is equal to 1. And so if cosh were a big old x squared minus big old y for sinh squared, what kind of object is this?
Hyperbola.
It's a hyperbola in the plane, right? It would be like this, right here. -1, -1, and 1, right? And so that's my claim. Let's prove it. Let's prove that it's true. This is why there's an h there. That's because it's a hyperbola. So just by definition, we have cosh squared sinh squared. So that's e to the x plus e to the minus x over 2 squared. E to the x minus e to the minus x all over 2, quantity squared. When I square this, I get a 4 in the denominator, minus ditto over here, 4 in the denominator. Now we need to square that out. E to the x plus e to the negative x times e to the x plus e to the negative x. First, outer, inner, last.
So
We get
the 2x
e to the 2x
plus 2e to the negative
No, it's just
No.
E, right?
Yeah, because let's look at this. The outer inner gives you e to the x times
Oh,
e to the
yeah.
negative x, which is the same thing as e to the x times 1 over e to the x. So that's just 1. So the outer gives you 1. The inner gives you 1. 1 plus 1 is 2. Everybody got that?
Yeah.
Yes.
Right? Outer is 1, inner is 1. 1 plus 1 is 2. Now the last gives you e to the negative x times e to the negative x.
So D negative 2.
E to the negative 2x. Negative 2x. Okay, now, here, same thing. The only difference is now we have minuses. So, first gives me e to the 2x. Outside gives me minus 1. Inside gives me minus 1. Minus 1. Minus 1 is minus 2 last time I checked. Minus 2.
Plus e to the negative.
Plus, good, plus e to the negative 2x. That's all common denominator.
Okay.
And so what I'm going to do, I'm going to extend this denominator. I'm going to extend this and do like that. Now I'm going to minus off all of that stuff. Everybody okay with that?
Yeah.
Did that work? Okay. So that is equal to this, which is equal to, let's see, the e minus e to the 2x is gone. E to the negative 2x minus e to the negative 2x is also gone. All that we're left with is 2 minus negative 2 all over 4, which is positive 4 over 4, which is 1. And so, yeah, that works. That's why they're called the hyperbolic trig functions, because if you think about this thing, cosh t as x and sinh t as y, then these are hyperbolas. This is how you parameterize a hyperbola. Okay. Let's take some derivatives. What's the derivative of cosh? So that's a constant. That 1/2 is a constant. Okay, so let's just take the derivative of this part. What's the derivative of that?
E to the x.
Okay, e to the x.
Plus negative E.
Minus e to the
Yeah.
Plus, so we could write it as minus e to the negative x, which is e to the x minus e to the negative x all over 2, which is what?
Cosh.
Sinh.
Oh.
Okay.
Okay, now let's take sinh. Let's take the derivative of sinh. Again, that's 1/2.
Negative cosh.
Is it negative? Oops. Positive minus e to the. Oops. Let's take the derivative. So we have 1/2 times. What's the derivative of the first thing?
E to the x.
Just e to the x. Take
Plus e to the negative.
plus e to the negative x, which is e to the x plus e to the negative x all over 2, which is just cosh. So it doesn't do the weird negative thing. It's just the derivative one is the other. And the derivative of the other is the one. It doesn't have to go through this 4-cycle loop. It's just a 2-cycle loop to do it. Take derivative of cosh, you get sinh. Take the second derivative and you're back to cosh. Ditto with this. Okay? There's one other thing that we need to know. Then now you're like, how's this going to help me? Well, I haven't even told you what today is. So, okay, there's one other thing that's going to help us. I don't think it's good. This may help you in your homework. I don't know. It may or may not. But there is one other thing that's going to help us prove what we want to prove today. I want to know what's arc sinh. I want to find the inverse sinh. So what I'm going to do is this. I'm going to say, let's say this is this, minus e to the negative x. I want to exchange the roles of x and y. So I have y equals e to the x minus e to the negative x all over 2. What do you want to do?
Multiply by 2.
Multiply by 2. That's where I would start with this. And one thing I'm going to do right now is I'm going to rewrite this like this.
Log, probably.
Log ain't going to help you yet.
Oh, yeah. Wait.
Do you have a
Yeah,
denominator?
we can factor.
So multiply both sides by e.
Let's multiply both sides by e to the x. This is e to the x, but he gets multiplied by e to the x, so he's e to the x squared. And this is just 1.
So it'd be the 2x. Oh, we can factor that though.
Let me write it this way, and let me see if you guys
Add
can
the
think
1
of-
and then divide by.
You're making this way
Wait,
harder
no.
than it needs to be.
Oh,
Does this have a form that we know how to deal with?
yes. It's a
Yeah.
polynomial.
It's just, yeah, and if we just say that's a, right, or like this is like some variable u squared minus 2y times u minus 1 equals 0, we could use the quadratic formula.
Yeah.
So let's use the quadratic formula, and I'm going to say, now if this were, I'm not going to do this, but if we had some,
So why is the
I don't know, how about like v squared minus 2y v minus 1? I would say that v equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right?
Okay,
And I would write it like v equals negative b plus or minus all this. But it's not v that we have, it's e to the x.
yeah.
So I'm going to say e to the x is equal to, and now let's do it. So,
So b is just negative 2y.
yeah.
Okay.
b is negative 2y. So negative b is just 2y plus or minus the square root of b squared, negative 2y squared, is positive 4y squared, minus 4 times a is 1, c is negative 1,
So just plus.
so plus 4 all over 2, a is 1, so there we go. Now I can simplify this by pulling out 4,
Yeah.
and that gives me 4 times y squared plus 1, which is root 4 root y squared plus 1. So that's just 2. So this is the same thing as 2y plus or minus 2 root y squared plus 1 all over 2, which is that and that divide, we get y plus or minus root y squared plus 1. Now we're almost there. We have that e to the x
So now we take all
is equal to y plus or minus the square root of
y squared plus 1.
y squared plus 1. And now, let's just stop for a second and think about this. This is saying you plug any number into e to the x and out pops this stuff. Can this ever be negative?
No. No.
Not unless you're using complex numbers. As long as x is a real number, we're going to assume x is a real number. If x is a real number, then this is positive. And if this is positive, that must be true. Okay? Now, let's just think about this. If that's minus, could that ever be true? Is y... No, this is never going to be true if that has to be positive. So we're going to throw that solution away and say, okay, this will always be true if y is any real number.
So it's just y plus
Yeah. So yes, so given that x is a real number, because we're only dealing with real numbers, guys, please try to keep it down. We're going to say this part, the minus part, would give us the complex numbers, which we don't care about right now. So it's going to have to be this right here. That's always going to be a positive number, no matter what. Even if y is negative, right? Like negative 2 plus negative 2 squared plus 1 is negative 2 plus root 4 and 1 is 5. That's bigger than 0. Right? So, okay, we should be good to go. Now, how do we get x by itself?
log of both sides.
Log of both sides. I take the log of this to give me that. I take the log of this to give me that. Y plus root y squared plus 1. And so, that is what we're looking for. Arc sinh. Guys, please keep it down. If you want to be loud, please go to your room. Is natural log of y plus y squared plus 1. Just like that. And it doesn't need to be y, we could call it u. Arc sinh of whatever your variable is log u plus root u squared plus 1. Okay, so we're back. Yeah, and so you can put a smiley face in there. As long as you put a smiley face there and there, you're good to go. Okay, we're just gonna use this later. We're just gonna say arc sinh is this, and so that'll give us what we want. You're probably not gonna need this for your homework. You may need to know the other stuff that we did. Probably not the inverses, but maybe, and you'll see how when I go to do what we're going to do in a minute. The subject for today is arc length. So that's, you have some curve. And we want to know, how long is that curve? The length.
Stretched it out.
What is, like if you were to stretch it out and make it flat, what would be the straight line distance of that thing? Now, what we're going to do is say, okay, let's suppose, instead of the entire curve, well, let's just say that we're on some interval A to B, and we want to know what is the length of that. One thing we could do, what we did in the Army, was, if you're trying, right, you're right, we train like we fight. What we do is you take a piece of paper, oops, I don't want to give anything away. I don't want to hang this up there. Let's just get a piece of paper. Let's do this. All right. You'd say, okay, I want to know, like this is a road on a map, and we want to know how far do we have to walk down this road? And it's curvy, so what you do is you say, okay, what I'm going to do is make a mark right here, and then go, I don't know, about to here until it starts to curve, and make a mark there. And then I'm going to tilt it a little bit and make, oh, it's nice and flat right there. I'll make a mark right there. And then as long as my mark's touching right there, I'll do here to here. And then we'll go, I don't know, this is pretty bad. We'll go right there, like that. And my paper's not long enough. But you would do something like that. And then if your paper were long enough, you'd do the last bit. And then you would just measure that right there. You'd have some legend on the side of your map which says this is 1 mile. And you'd say, okay, from there to there is that many miles. We don't have that here, but we could do something similar and say, you know what I did? Between each one of those, I used a straight line to go from here to here. I used a straight line to go from here to here. I used a straight line to go from here to here. I used a straight line to go from here to here. Ditto from here to here, and finally from there to there. And each one of those lengths, right? So the first length was this right here, from there to there. We'll call that L1. The second length was from here to here. We'll call that L2, and so on. We have, here's L1, L2, da-da-da-da-da-da. We have the ith one right there, Li. And finally, we'll say N, because we chopped this thing, apparently, up into N pieces. And so then, we could say, okay, then the actual length that we're looking for, let's call it capital L, is approximated, we can approximate it by adding up all of those bits right there. So in other words, I take the sum as I goes from 1 up to n of all of the lengths, yeah? That's what I did, but now I've just formalized it right here. I said, all right, this is essentially the same thing as the paper method, right? We had nothing like this in the Army. Okay, so, okay, now here's the thing. What did I do? I didn't say this explicitly, but we partitioned the domain. Right? Does this sound familiar? You have some interval from A to B, and you chop it up into n pieces, and then you add something up. Sounds familiar, doesn't it?
Yes.
And now imagine what we're going to do next.
Let n go down.
We're gonna say, well, you know, you would get a better approximation if you chopped it up into finer and finer pieces. In other words, then we're gonna say, actually, let's define the arc length to be the limit as n goes to infinity of this sum right here, as I goes from 1 to n of all of the individual little lengths. Does that make sense? You guys believe it? I mean, like, it should, this crazy definition that I just wrote down actually conforms to what we think about as the length of a curve, right? Okay. So let's calculate what this thing would actually be. And let's say that this function here is f of x. And just to make notation simple, I'm going to go ahead and call it y. The y's are my outputs. So when I'm here at x sub I get out some y sub I. When I'm here at, pretend those aren't there, xi plus 1, I get out some yi plus 1. And let's figure out this length right here. So I'm going to go ahead and zoom in on this right here. We're at xi plus 1. We have some output yi given by the function, right? Yi is what I get out when I plug in an xi, right? And then I have some other output yi plus 1 when I plug that in. And now the line that I drew between them is that line right there, Li. So what's the length?
What's
xi plus 1 minus, no, the slope would be y of I plus 1 over.
Yeah, so I'm thinking about triangles, right?
Oh, just do that.
Yeah. And so this is what I'm going to do. I'm going to say the height here is yi plus 1 minus yi. Or let's just call it delta y. Can we just call it delta y? It would be easier. And it's nice because if we just call it delta y, that all these delta x's can be the same length. Right? Because we're going to imagine that we partitioned it equally, right? That our delta x, which is b minus a over n, right? Remember from the definition of that guy?
Yeah.
That's how, with an integral, that's how we do this. So that's just delta x, okay? Okay. Understand, we're still talking about the ith one, but now we don't need the I. This is what we're dealing with, okay? So you tell me, what do I need to do to find that actual length?
the
Square y squared.
delta x squared.
Yeah.
So, okay, delta x squared plus
Delta y squared.
delta y squared is equal to what?
L
squared.
squared.
Li squared. And so what's Li itself?
The square root.
The square root of that. Okay, so then Li, and we're going to take the positive square root because we're talking about lengths. And in this scenario, we want to think about length as positive. Okay? So, there we go. Ready? Let's do it. Okay, so this, and actually, everybody got this picture in their head, this is the thing we're dealing with. I want to go ahead and get rid of that. And say, okay, I still want this up there. Y is equal to x for some function. And we have this definition. L is equal to the limit as n goes to infinity of the sum I goes from 1 to n of the LI's. Okay. But now we have found that each of those individual LI's are equal to this. So, this gives me the limit as n goes to infinity of the sum of, I goes from 1 to n, of this stuff right here. The square root of delta x squared plus delta y squared. And we understand that we've chosen delta x so that as n goes to infinity, delta x gets infinitely smaller. Is this thing an integral?
I don't know. It just goes to dx.
Not all limits of sums are integrals. Here's a limit of a sum that's not an integral. I equals 1 up to n of I squared. That thing does not converge. And if you took the limit as n goes to infinity, you would have 1 plus 2 squared plus 3 squared plus... It would blow up. Can you guys please play with that in the other room? Please? If you're going to play with that out here, that's really loud, and I'd appreciate it if you went to the other room. So,
Yeah.
but now, 1 second here, because something squared as the limit of a sum, in other words, we know that if you took the integral of, say, x squared, you would have 1/3 x cubed. So, but we're missing something from here. It's not just that the thing's blowing up, right? What keeps this if we had the sum for something squared?
Delta.
Delta x. We need to, this doesn't blow up if we have a delta x to keep him small, because delta x gets really, really, really small. In which case you get the dx there, which then does give you that. But it's only because the delta x is getting really, really small to keep this thing tame. Otherwise, you're adding up infinitely many things that may or may not blow up, depending, right? Here, we don't have a delta x to tame this right here.
But it's the square root.
But there's a delta x
Yeah.
in there.
And the delta.
Maybe we could get that delta x to come out. Because as it stands right now, this thing is not an integral. We have to have that we have to have the height of something multiplied by the width of something, and that width of something needs to be delta x.
Yeah.
But I see a delta x in there. That's like, I could probably, what could I do?
You could factor it out.
I could factor it out. Let's try. Let's just see what happens if I try to factor that guy out. Okay. So I'm going to factor out the delta x squared.
And it's
Delta x
delta
squared.
y squared over delta x.
Okay, so I have 1 plus delta y squared over delta x squared. Now, that guy pops out.
And it's
I'm going to go to the limit of the sum, and I'm going to be really explicit about this because I don't want to mess this up. Delta y quantity squared, delta x quantity squared. This is delta x squared, square root of it. And by design, delta x is already positive, so we don't need to worry about it, right? He just comes out as delta x. So we have the limit as n goes to infinity. I is 1 up to n of, now we have 1 plus delta y squared delta x squared times the thing that we need, delta x. Now in the limit, well, first off, can I rewrite this as like one thing?
Get a common denominator.
Hold up, I'm just talking about this part. Instead of writing this as something squared
just delta
over
y over delta x squared.
Yeah, it'll be a little bit simpler to just write it like this. So we have delta y over delta x quantity squared. So I'm just gonna go. Can I just do that?
Yeah.
I'm just gonna do this and say, okay, hold up. Each one of those squared is the same thing as just doing them squared. I haven't changed anything, just wrote it a little bit differently, okay? Because that's that, yeah, okay. But then as n goes to infinity, think about what we did here. We had our xi plus 1, or xi plus 1. We had our yi's. As delta x goes to 0, which is what happens when n goes to infinity, delta x goes to 0. Delta y also goes to 0, and he happens to be the slope of the line. This thing is dy dx.
Oh.
That's dy dx. That's the derivative of the thing, right?
Yeah.
Because remember, this bit
This
right
is
here
something.
is f of x, and so that is the derivative of f. That's f prime,
Yeah.
or dy dx, right? They're the same thing. So we could say then, this goes to the integral of this stuff, 1 plus, and just like we do with when we take the limit, we rewrite the delta x as dx, dy dx. From where to where? Where were we integrating from? What was our domain?
A to B.
From A to B. And so we could, there's your answer, or you could rewrite it A to B root 1 plus f prime of x squared dx.
So that's how you find arc length.
That is the arc length. When you define length by the Euclidean distance. Remember, our assumption here was, how do we find that length right there? Well, and you told me, well, it's this squared plus this squared equals the length squared. As long as that's your definition of distance, this is your definition of arc length. If that changes, which it can in different spaces and whatnot, like if you have a curved space, like what's your distance on a globe? It ain't that, right?
Yeah, how does that?
Yeah, well, yeah, you need to take a ton of math to get there, right? Because if you say, well, the straight line distance from here to here, well, that cuts through the thing. So that's not, then this no longer is your distance from there to there. You would have a different function. But this is what you would do still. You would take whatever your distance function is. Hopefully, you could do some magic with it to pull out a delta x and rewrite it in terms of an integral. Otherwise, good luck. And there have probably been many PhDs awarded to people who figured out how to find the arc length of something in some crazy space that blah, 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 blah. But this is it, right here.
Isn't there some, like, I don't know if it's a paradox, but it's like when you're taking the, like, length of the coastline or something, and it's, like, infinite. 'Cause there's so
Yeah,
much-
like where does the coast end, right? Like, if you look at a map, here's England. Nice, England. Right? If you look at a map, you can say, oh yeah, that's where that's the arc length. But then as you zoom in on it, right, it gets more and more jagged, right? And you zoom in on that, and it's even more and more jagged. And at some point, you have grains of sand, and it's like, well, do you go around this grain of sand and there, and blah 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 blah. That's that, yeah. But that's more just doesn't have so much to do with how you're measuring distance. That's just one of those, like, where's the line, you know? And if you look at like a fractal, you know, you guys know fractals,
Yes.
Yeah.
right? If you look at one of those, the actual boundary is infinite, and as you zoom in, it gets more and more jagged, and you zoom in, and it's more and more jagged. So you can never actually measure any length from one thing to another. But here, we've assumed, and I didn't say this, we assumed, right here, here's your assumption, that f is differentiable. Otherwise, this ain't gonna work.
Yeah.
If f doesn't have derivatives, however, if f is continuous, because remember, if you're differentiable, you're automatically continuous.
Yeah.
But you could be continuous and not differentiable. Like, here's a continuous function that's not differentiable at those points, at the peaks and valleys. But what you could do is stitch it together and say, well, you are differentiable from here to here. And so we could get your length from there to there. You are differentiable from here to here, so we could find your length from there to there, and so on and so forth. So really, all we need is for f to be continuous. Unless he's not differentiable at infinitely many points, which, have fun with those functions. Something, the Weierstrass function, if you want to look into that. Weierstrass. That's two S's, by the way. The Weierstrass function is famously not differentiable anywhere because it's infinitely jagged. It's another one of those that if you zoomed in on it, right, it looks like this. And if you zoomed in on it right here where it looks flat, it's actually more and more jagged. And then you zoom in on any of those and they're just more and more jagged forever. And so that would be a function that fails this. It's like you can't do that. All the functions we care about, they have this nice nifty property right here. And you could get their Euclidean length.
And could you graph the wires? Like what's the
You can, but it
Is there an equation for it?
look it up.
Okay.
It has to do with the sum of sines and cosines. In fact, I could give you just right now. We'll just go ahead and do this real quick. This isn't it exactly, and there's like a bunch of Weierstrass functions. They have to do with this. You have the infinite sum as n goes from say 1 to infinity. Here's your f of x, and it has something like this. It's like you could do it like this. You have to have it over like an n, but then if you do an n squared in here. And that's perfectly good. He converges. He's a nice continuous function. If you add these guys up, so what you're doing is you're getting, this is sine x plus sine 4x over 2 plus sine 9x over 3 and so on. This converges because these guys get small and small and small and small, and it converges to a nice continuous function. But if you try to take its derivative, let's see, what's the derivative of sine?
Cosine.
Okay, so it's cosine of stuff
Times,
the derivative of the inside stuff,
which is
n
n
squared. No.
Yeah.
N squared is a
Yeah.
constant with respect to x. Yeah. And so then the n cancels one of these, and now you have the sum of this guy, n, as n goes from, is it 1? Yeah, in this case it would be 1 to infinity, cosine n squared x. And this bad boy blows up. He blows up bad. So go on Desmos and graph this guy, and you'll see. I'm not sure if this technically satisfies it, because there's certain things about n, it has to be within some whatever to be a Weierstrass function, but this will have the property that I'm talking about, that as you zoom in on it, like when you first graph it, it's going to look something like this. It's going to look like that. And then you're like, oh, it's nice and flat right here. And then you zoom in on that, and it's going to get crazy and crazy and crazy. And it's, yeah, interesting. So this thing would not be a good candidate for this because he's not differentiable. And so good luck plugging in his derivative. He doesn't have one. So that's not going to work. But all the functions we care about work. And they don't necessarily need to be differentiable. Like I said, if they're not differentiable at finitely many points, or possibly more, then you should be good. Just as long as then you're adding up a bunch of integrals. We're not going to see any of that. So here we go. That's arc length. Let's do an example. Find circumference of a circle of radius r. It should be circumference is 2 pi r. Let's prove that. Now, what I'm going to do is say, okay, the entire circle is a bit more than I want to deal with. I hope Let's just do this bit right here. Let's just do that. And then I think we could all agree that if I multiply that by 4,
Yeah.
I'll get it. Right? Okay, so that's what I'm going to do. I'm going to say, okay, we have some function, which is just the part of the circle we care about in the first quadrant, from 0 up to where?
R.
R. Good. Right? Now, what is that function?
The square root of
The square root of
1
Yeah.
1?
R squared
R squared
minus x squared.
X squared, that should be it. Let's just double check. Because in general, it's x squared plus y squared equals the radius squared.
Yeah.
The y is r squared minus x squared. I take the square root. I'm going to take the positive square root because we're up there, making my life a lot easier. And so what I'm looking for is the arc length of this function from 0 up to r of this stuff. And so I'm going to use, and I'm going to call it L, the arc length from 0 up to r of square root of 1 plus f prime of x squared dx. So, we're going to need f prime. What's f prime?
Well, that's the 1/2. So there's
1 over 2 root r squared minus x squared
There we go.
times
Times
negative 2x.
negative 2x. So, he's gone, he's gone. Now, let's do that. 0 up to r, root 1 plus that stuff squared. X root r squared minus x squared dx.
Yeah, and x squared.
Yeah, okay, so let's see. Hold up. Let's see what we can do here. X squared, so that's 1 plus x squared over r squared minus x squared.
Yeah.
A bunch of different ways we could go with this, but I would like to rewrite this with that denominator. So I'm going to go r squared minus x squared over r squared minus x squared. Now we have a common denominator.
Oh, and then they go x squared's cancel.
That's going to be nice, huh? Alright, so the common denominator is r squared minus x squared. What was in the numerator was r squared minus x squared minus x squared plus x squared dx. Integral. The x's are gone. We have r squared over r squared minus x squared dx. I'm gonna be really explicit here. Here's that. Here's that.
Yeah.
R squared, that's a constant. And so I'm gonna pull him out as just r, right? Okay. Dx over root r squared minus x squared. Now there's a bunch of different ways we could deal with this.
Trig substitution.
That's what I'm thinking. And I just know from experience, the way I like, we could go ahead and draw a triangle with an R and an X and etc. That's one way of doing it. The way that I did it, when I did this, whenever I did it, was bringing this back up because we're running out of room. I like to do it this way, where I just factor out my R squared out of 1 minus X squared over R squared. Yeah?
Okay, then the R's cancel.
And then the R's are going to cancel, so that's kind of nice. So let's do that. I bring that out. We have R on the outside. This is dx. That's the same thing as root R squared times root 1 minus X over R quantity squared. Yeah?
Yeah.
Right?
Yeah.
Check me on that. I don't want to mess that up. So then the R squared is just R. And this is the root. Is that minus? Yeah, it should be minus, right?
Yeah.
Yeah, okay. 1 minus X over R squared, dx is there, R comes out, cancels, and we have
Cosh.
dx root 1 minus x over r quantity squared. I feel like doing a u substitution.
Yeah, it's like the
Oh.
arctangent
U equals x over
Yeah. And then du
Cosh.
equals 1 over r.
dx over r, 1 over r dx. And so r du is dx. So let's get rid of that. Dx is now r du. This is 1 minus root 1 minus u squared.
plus
That's
r.
r du over root 1 minus u squared. Okay. Whew. What's that?
Wait, that is arc
Ow.
something arctangent. Wait,
Right?
I think arcsine.
And that's when I was doing this, I was like, wait, is this arc sine or arc cosine? And then I was just like, you know what? Let's just do it. Just do the u substitution. Because I just couldn't remember. So I'm going to say, okay, I'm going to let u be here.
It's not arctangent.
And I want to let that be 1. And then I'm going to say, okay, 1 minus u squared. Like that. So now, sine, and the reason I like my u there is because now my sine theta is u. And my du is cosine. I don't have to worry about negatives. Okay? So the du is going to get replaced with that. Now I need a 1 over that. Well, hold on. Cosine theta is 1 minus u squared over 1. So 1 over 1 minus u squared is 1 over cosine, which is secant. But I'm not going to write it like that. Because I get my r. I get my du, which is cosine theta d theta.
Oh no, it's just cancel.
1 over that is 1 over cosine. Or I could just, I could just look at it and go, that thing right there is that thing right there. That thing is cosine. So cosine goes there. Although, I mean, the way that I usually do it is like this, and this is the way we've done it in class. Right? Where I say, okay, then that part's the 1 over cosine.
Yeah.
And then the du is cosine d theta. They cancel. At any rate, they cancel. And what I get, I'm going to lose that, is r 1 d theta. What's the antiderivative of d theta?
Just take
Just theta. But theta is
sinus
Arc
theta.
u.
arc sine u.
Oh, okay.
Right? Arc sine u.
Yeah.
Right? How do you get theta to pop out? Well, you take arc sine of both sides.
Yeah.
So that's r arc sine u. U was, we lost him, u was x over r. So this is r arc sine x over r. Now that we're back in x, I'm going to bring my stuff back. We integrated from 0 up to r. So, from 0 up to r, and now let's get rid of this stuff. Now I've got all my substitutions back. I don't need any of this. And I'm going to say, okay, so we had that the limit, stop it, was from 0 up to r of the stuff, which we found is r arc sine x over r up at r and down at 0. So that's r times, plug in the r, I get arc sine r over r minus arc sine 0 over r, which is 0. What's arc, so that's arc sine 1. What's arc sine 1?
No.
Pi over 2.
Yeah. No,
Yeah, let's just make sure. Here's arc sine does this, comes down, plug in a 1, get out a pi over 2. So that's pi over 2, I lost my r, stop it, minus 0. So r times pi over 2 equals L. R times pi over 2 is equal to L. And you're like, that's not the circumference of a circle.
Oh, times 4.
Oh, yeah. Okay, but C equals 4L, which is 4 times R times pi over 2, which that divides that, and we get 2 times R times pi, or 2 pi R, as desired.
There's a lot of ways to do this.
Okay, are you guys ready for the main event? Okay. This is what your homework is. There's that, and I only gave you the stuff where they just say, find the arc length. There's a bunch of other stuff that I don't care about. And like, we're at the end of the year, we're gonna be just it's gonna be touch and go. Just like, you should know this. You should know arc length. Okay, and that's what we're doing. Now you know arc length. And you're gonna have 9 problems to play with. Here's the main event. Here we go. All right. On a plane, very important that we're on a plane. So we're on a plane. Here's my plane. It looks like this. Here are 2 points. A up to B. And they could be anywhere. I just happen to put them in the first quadrant. A happens to be there, B happens to be there. They could have been anywhere. Any 2 points on a plane. Here's my question. What is the shortest path from A to B?
Straight line.
You say it's a straight line.
Isn't it like Socrates or something?
Good for him. There we go. Let's prove it. I believe it's true. I believe that it is true that the shortest path, in other words, the shortest length from A to B is a straight line. Now, again, on a globe, that's not true, because if A is over here and B is over here, the straight line would tunnel through the globe. If you're on a globe, it's not a straight line, it would be a curve. It would be an arc, right? Okay, but we're on a plane, and so how could it be anything other than a straight line? Well, I would like to prove this from first principles. Okay? Everybody with me? We're going to make 3 assumptions here. Stop. Besides all, stop it, stop. You guys, go into one of your rooms and play, please. Here are the 3 assumptions. So all of this, we're assuming that we're on a plane and there's 2 points on the plane. Here are some extra assumptions. We're going to assume that a path from A to B is a function. Now this seems reasonable. Why? Because you can't be in 2 places at once. So if you're going from A to B, right, then you can't have 2 outputs here. If we're going to think about this as my x, my input axis here, my x input, if you're at any point along here, I don't care which path you took, you can't be at 2 simultaneous places in the y direction. Right? Okay, so that's a pretty reasonable assumption that the path itself is going to be a function. Yeah? Okay, that's reasonable. Now, I'm also going to assume that the path is continuous. Why? Because you can't disappear and reappear somewhere else, right? Like in the real world, this is what we're talking about walking, right? This is what we're thinking about. You're walking from A to B. Like you can't just magically pop up here.
It doesn't work.
That doesn't work, right? So the path is going to be continuous. You will be able to walk it without teleporting or using warp drive or something like that. Okay, so everybody okay with that assumption?
Yes.
Not assuming too much here, right? Okay. Here's where I might be assuming a bit too much. That the path is differentiable. Now, how could it be continuous and not differentiable? Well, you could do something like this.
Yeah.
That's a continuous path, but it's not differentiable. Here's a continuous path, and it's not differentiable.
But you can't really.
I mean, now we could get in there and start arguing, like, I mean, you could walk that way. Maybe that way's quicker.
You can't have a turn exactly. Like,
Right, really, honestly, if you're walking, you can't, you could.
I guess you could
You
just
could.
stop and then turn.
You
and
could
then-
stop, because we're not talking about time here.
Yeah.
Time is not your input axis. We're talking about the actual place that you're going. In the x, which is, I don't know, east, and the output's north, you could stop and turn. But I doubt that any path that's not differentiable is going to give you the shortest one, because you're changing directions. So maybe I'm assuming a bit too much with this, but it does seem reasonable, does it not, that we could say it's probably smooth. Like, the shortest one's gotta be the smooth one. If it's not smooth, you're probably taking more than you need.
Yeah.
Okay, so that's all I'm gonna assume here. Okay, get ready. I'm about to blow your brain to the back of the auditorium. Watch this. So, we have some function. Those were my assumptions, right? That this path that we're looking for, we don't know what it is, but it can be described by some differentiable function f. If that's the case, then the length is given by, let's have a little bit of room here. It's given by, now what I'm going to do is say, you pick your favorite axis. It doesn't matter which is y and which is x. I'm just going to, whichever one is down here, I'm going to call x. And I'm going to write a, the little a is the leftward starting point. And that little b corresponds to the x value of the big B, right?
Yeah.
So then the length that I'm looking for goes from A to B, and he has this form. F prime x squared dx. That's the length, yeah? Here's my question to you. L is a function of something. What's it a function of?
F. Wait, X.
Check this out. X squared dx from, I don't know, how about 0 to 1? Is that a function of x?
No.
No, because watch what happens. You say, well, that's 1/3 x cubed, evaluated up at 1 and 0. That's 1/3. Minus 0 is 1/3. Watch this. 0 to 1, t squared dt is 1/3 t cubed at 1 and 0 is just 1/3. Did it matter what x or t was? So if I said here's y, it's not a function of x.
Yeah.
It would be a function of something if I maybe made the top like how about a z? Then you could say it does matter, because then you're gonna get your z cubed minus 0 is just so then that thing would be a function of z. But here both a and b are constants, right?
But there's the f of x.
Say again?
There's an f of x in there. Which
Yeah,
is,
it won't matter.
okay. So it's not a function.
It's a function of something, but it's not x. This is a function of the function that you're using.
Of f of x. Wait.
L of f. Is your mind blown yet? See, the distance, the actual distance does not change between A and B. that is always the same. A and B are fixed. You're not changing that. The only thing you can change is your path, right?
Which was that?
If you, so for instance, if you let your f be x squared, then you're going to get from A to B one way. But if you let f of x be, I don't know, root x plus 1, you're going to get there another way. And the thing that varies is the way that you go. It's f. F is your variable. F is the input to this function. Does that make sense?
Yeah.
The thing that changes, the only thing you can change in this setup, because remember, A to B are fixed, right? You're given an A and you're given a B. And somebody asks you, what's the quickest path? What's the shortest path to get from there to there? Well, the path, that's the input. That's the variable. That's the thing that you want to change. So this length is a function of the path. It's the function of f. Now, to prevent our brains from being completely broken when we start to manipulate this thing symbolically, I'm going to say, let's call this y. So now, L of f is going to be L of y. 1 second.
Yes.
Does it make sense that the thing that changes, the variable, the thing that is changing,
Yeah.
is the path itself?
Yeah. Which is f of x. Or y, I guess.
It's y, right? And so now let's rewrite this guy in Leibniz notation, dy dx, right there, dx. So this is a function of y, and this is a length as a function of y. How do we find the shortest length? Don't look at all this.
Oh, so
you have
0.
you set what to 0?
The derivative to 0.
There you go. So in other words, I'm going to take the derivative with respect to y and set it equal to 0. Then I'm going to solve for y and figure out what gives me that, right? That's how you find, that's how you optimize something. What are we optimizing? Length. My output is length. And so if I take the derivative of that with respect to y, set that equal to 0, I'll find the y that gives me that minimum or maximum length. Pretty obvious that it can't be a maximum length. Because I could take, like,
go the other direction.
yeah, like, I mean, I could take successive sines, you know, like, if I do like a sine, and then whatever the outputs would have to be, so it would be some kind of a plus, well, I don't know if it's a and b, but then I could do this with like any x, so that, I mean, any n in there. So it could go infinitely, I mean, technically as many times as you want to get from there to there, right? So, then it would probably be a, b minus a, something like that.
Oh, yeah.
Yeah, something like that. Anyway, so when we do this, we will find the minimum length. Okay? Everybody with me on that?
Yeah.
Okay, so then what are we going to need to do? So what did I just say? We'll take the derivative, and I want to go ahead and do this.
Take the derivative of the integral.
With respect to what?
Oh.
So there's my function, and I'm taking the derivative with respect to, what's my input?
Y.
Y. So I want dl dy. I'm going to take the derivative with respect to y of this function. dy dx squared dx.
So the integral.
It turns out,
Wait.
no,
Never
because
mind.
it's dy. And you think, oh, easy. No, not at all. And it turns out that what we have to do is switch, and in this case you can, because remember, this is just a sum. It's a limit of a sum. And we're taking the derivative of something. And so in this case, it turns out that yes, we can switch the order and go dy of the stuff. Right?
Yeah.
Right? Because if you have like e to the x plus sine x plus a bunch of other things, that's some function. Right? That's a sum of things. And you take the derivative of it, you can distribute that in and take the derivative of them individually. That's what we're going to do here. We're going to change the order here. We're going to bring the derivative in and take the derivative. We're going to say, okay, and notice I'm dropping my limits of integration. They won't matter at all. Because they didn't matter, did they? Like, we didn't say there were 7 and 5, like who cares? So I need to take the derivative and look at how I'm writing that. Yeah? You like that? You like that? Like, take the derivative of this thing. What do we do?
dx, right?
Huh? Oh, yes, oh, thank you. Yes, that would have really messed everything up. Okay, so, yes, so it's going to be the integral of over 2 root stuff times the derivative of this, which is going to be 2 times that stuff times the derivative of the inside stuff. So dy of the inside stuff. So now let's put everything in there. Okay, so we had dy dx. So in here you have 1 plus dy dx squared. Same thing in here. Dy dx. Here's the hard part. Dy dx. And like I said at the beginning, you have dy dx. You take the derivative with respect to y. We've got to use a chain rule. And we'll take the second derivative and then multiply by dx dy. Okay, so let me clean this up a little bit. The 2's cancel, and on the top we have dy dx times d squared y dx squared times dx dy. All over. Stop messing with your brother. Stop it, Peter. dx on the outside. Is that good? Everybody got that?
Yeah. Now it seems to have canceled.
Now a bunch of these cancel. We could bring this one into the mix, whatever. It'll be nice to have him later. Those cancel. Those cancel. And now we have the integral of d squared y dx squared all over 1 plus dy dx quantity squared dx.
Okay.
I feel like a u substitution is going to be good right now. Why? Because, well, I see something that's in something. And I see its derivative that's just sitting out there in the numerator.
Oh, yeah.
You know? Like, we've seen this before, right? Like, if we had this, 1 plus, I don't know, sine squared, and I saw a cosine up here, I would say, hold up. So the derivative of sine is cosine. If I let u equal sine, then du equals cosine dx. Cosine dx, and then now he'd be gone. That's kind of what we're in right now. We have something in the inside, and its derivative is out here in the numerator. That's what's making me think that that's going to be a good idea. So I'm going to go ahead and do that. I'm going to say, let u equal dy dx, so that du equals d squared y dx squared. I'm sorry, this is all running together. But you like that?
Yes.
Times dx. Don't forget that. Okay. So really, we just had some derivative of a function. Like y was like, I don't know, 3 cosine x. dy was negative 3 sine x. And now we took its next derivative. D squared y dx squared is then just the next derivative, which would be negative 3 cosine. That's all we have. That's all that means. We have some function, it's already a derivative, whatever. Then we take its derivative, we just take its next derivative. That's all that's going on there.
Okay.
Everybody with me?
Yeah.
Okay, so now I'm going to come over here and say, okay, so that's the integral of the square root of 1 plus u squared, right? Because u is dy dx. Du is d squared y dx squared dx. Isn't that all of that stuff right there?
Yeah.
So I'm just going to replace dx, I'm sorry, all of this with du. Everybody buy that? I didn't mess anything up, did I? Okay. What do you want to do with that?
It's just arc sine with u, right?
It's not.
Wait, what?
It's not. If it were minus
Right.
in here, it would be.
I forgot.
Yeah, I know. And this is, when you see that, you think trig sub, right? The plus is not going to help you. And you could try to figure out all day, how do I get a square root? Well, I guess 1 plus u squared, you'd have a 1 and a u. That would work. And maybe something like this, right? That's how that would work?
Yeah.
Something like that. And you're going to hate yourself in about 5 minutes. You're just going to be miserable. So what you do is you say, wait a minute, if trig sub makes me miserable, hyperbolic trig sub might not. And remember the thing. Now, we skipped this. We didn't do this. This was part of one of the things when we were doing the u substitution. I just decided not to do this. But it's the same kind of thing. But see, the thing with trig sub is it's nice because since the trig functions are on a circle, like, it lends itself to triangles really easily. Hyperbolas, good luck. I mean, there's all kinds of crazy stuff, and it's not, that doesn't work very well. So when it comes to hyperbolic trig substitution, I say it's very easy to say, well, hold up, let u equal sinh. Let v equal sinh u. You just you see that you have something like this. Take wait. No. This let u equal sinh v. There we go. So then what's du? What's the derivative of sinh? Cosh.
Yeah, so cosh.
Cosh v dv. Now this has the nifty property. Remember that cosh squared minus sinh squared equals 1.
Yeah.
So that cosh squared is equal to 1 plus sinh squared. So when you have a plus, this is why we did this in the first place, is because now we're going to let u squared be sinh squared, and now when I plug that guy in, watch what happens. du is now cosh v dv. Yeah? You got that?
Yeah.
1 plus u squared is the same thing as 1 plus sinh squared.
Yeah.
So this is just the square root of cosh squared v. Right? 1
Yeah,
plus sinh squared.
Oh, and everything cancels.
Yeah.
Isn't that great? So, hold up, let's just make sure. Because we had 1 plus u squared, which is the same thing as 1 plus squared. U is now sinh. So that's 1 plus sinh squared, which is cosh squared. V, yes. Now, cosh is always positive, so we don't need to worry about weird stuff. Remember, cosh is e to the x plus e to the negative x over 2. Positive, positive, positive. It's always positive. So we don't need to worry, as long as your inputs are real numbers. Yeah. So that's just cosh v over cosh v dv is just the integral, not right now, dv. Sorry, bud, just give me a minute.
Okay.
So what's the antiderivative of v?
Just
Or dv, I'm sorry. What's the antiderivative of 1 dv?
Just
V plus a constant.
okay, but v equals arc
But v, okay, so now here, let's see what I want to get rid of. So let me, over here, we need to hold on to all the stuff that we had, okay? We had that u was equal to dy dx. We have that u is equal to sinh v, which means that v is equal to arc sinh u, okay, so we need that. And I think I could get rid of all this other stuff. I can get rid of that, I can get rid of that, I could get rid of that. Okay, and we got all the way down, I already wrote that down, so I'm going to get rid of it. Okay, so, we got that this is equal to v plus a constant. But v is arc sinh u. Oh, and this is prime, by the way, right? We took the derivative. So this is, I'm sorry, d dy. So this is the thing that I've been looking for, dl dy, or L prime. Okay, which is arc sinh u plus a constant. Arc sinh, like I said before, arc sinh u is the same thing as log u plus square root u squared plus 1. Yeah. So, we have log u plus square root u squared plus 1 plus a constant. But u was dy dx. Log dy dx plus dy dx squared plus 1, all of that plus c. And we said that that is equal to dl dy.
Yeah.
Now, wait a second. Would you guys rather deal with this as dy dx or y prime of x? Because it means the same thing.
Yeah.
We'll just keep it like this. This will be alright. So, this is the derivative. What do we want to do to find the shortest whatever?
Set to 0.
Set this equal to 0. So let's set this equal to 0. Okay, now, when we set this equal to 0, and we want to find y of x, it makes this true. Well, let's get that dy dx by itself. How do I do that?
We need this. Do we need the c or?
We need that c. We don't know what it is. We need it because we have not evaluated it here at the endpoints.
Yeah. Okay.
We need the c to come along for the ride.
Yeah.
Let's get them over on one side.
So e like
Yeah. It looks like all is lost, really, but all is not lost. This is going to work out. Okay, how do I get stuff out of log? E to the stuff. So I'm going to go e to this stuff, e to that stuff. And I end up with dy dx plus the square root of dy dx squared plus 1 is equal to e to the negative c. That's a constant, isn't it? If c is a constant,
yeah.
then e to the negative c is some other constant. So let's just call it k, just to make things a little easier on our eyes. Here's just some constant k. Everybody with me?
Yeah.
Okay, I'm going to go ahead and get rid of all this stuff. I think we could just get rid of all of this. Here we go. Okay, almost there. So we have dy dx plus the square root of dy dx quantity squared plus 1 is equal to some constant k. It's a positive constant, but that won't matter. That won't matter. So the camera died. Let me finish up the lecture here. We have dy dx, which, remember, that's the derivative of the function we're looking for, right? So, in other words, right here we have a y prime, or an f prime if you like. And if we could get that thing by itself, then we'll be able to figure out what f, or y, the function which minimizes the distance, that we'll be able to get it. And so that's the idea. But so now I'm looking at this and I'm thinking, okay, I need to isolate the dy dx. Problem is it's in a square root and it's outside of a square root. So if I could square that, that'd be good, but if I square all of this, it's going to be ugly. So let's isolate the square root. So we have dy dx squared plus 1 equals, and I'm just going to bring him over. So k minus dy dx, like that. Now I can square both sides. I'm going to do that, square here, and I get dy dx, whatever that function is, squared plus 1, is equal to, now when I square this out, I get first outer inner last gives me k squared minus negative k dy dx, another negative k dy dx, for a total of negative 2k dy dx. Now finally plus dy dx quantity squared, that function squared. Now I could see something to cancel. That'll be really nice. Let's cancel this guy and that guy. Now I'm trying to isolate him, but there's a negative in front of him, so I like to make him positive. I'm going to take him over to this side of the equation. Add him over here and we get 2k dy dx. The k squared stays put, and I'm going to bring this 1 back over here. K squared minus 1. Almost got him all by himself. Dy dx, I'm just going to divide both sides by 2k. And there we go. Dy dx is equal to k squared minus 1 all over 2k. But remember, k is a constant, right? Because the way we got k, we substituted. We had a constant c. We took e to the negative c and said that's just a constant. So it's some number like 5. And then we square it, minus off 1, divide by 2, times it, whatever. Another thing to notice is it can never be 0, right? Unless c happens to be infinity, which it's not, but we could divide by it, no problem, because e to the negative c is never equal to 0. So we could divide by it, he's cool. So this is just some number, some real number. Let's give it a new name. The same way we did earlier with c. E to the negative c, we called it k. Let's give this a new name. How about let's just call it m. For some constant value m. Okay, so let's get this back up here and think. What do we need to do? What we have, after all that work, we found dy dx is equal to some constant m. Let's think about what this is. Dy dx is the derivative of the function itself. The derivative of our path. In other words, right, dy dx is y prime of x. So we have y prime of x equals sum m. So what's y? We took the derivative of something and got a constant. That function itself is going to have to be, I guess, x times that constant, right? Or we could see that by, let's integrate both sides with respect to x. Take x here, right? Since you're taking the derivative of y with respect to x, when you integrate with respect to x, you just get your y of x back. Now, you have a constant, take the antiderivative of a constant, and you just get m times whatever it is. Since we're doing dx, it must be x. Double check it and take the derivative of both sides. M times x, take the derivative of that, you just get m. Yes. Take the derivative of y with respect to x, you get y prime, or as we call it, dy dx. That's great. But now, you took the antiderivative of something, and so we're going to have plus a constant. Let's give it a name. How about b? Some constant b. And so it turns out that the path, our function, which gets us from point A to point B, that's the shortest distance, the shortest length of that path, has the form y equals mx plus b. So indeed, the shortest path on a plane between 2 points has the form y equals some constant x plus some constant b, i.e. it is a line. Now, one thing I was saying a minute ago, before the camera died, is that, again, we just want to note, like, I can construct a function which bounces up or back and forth arbitrarily many times. So, clearly there's no maximum length, right? So when we set our L prime of y equal to 0, we must have found a minimum, because there cannot be a maximum. Now, if you really want to go for it, you could take your original thing that we had right here, right, our root and all that, dx, and then you take two derivatives of it, plug this guy in at some point and check that yes, he is positive, and so concave up, that is, the function L of y is concave up. But I mean, we're getting into some really deep waters if you try to do that. It's much easier to just say, obviously there's no maximum, so the extreme value that we found when we set L prime of y equal to 0 must have been a minimum. And so we could conclude, yes, the shortest path from A to B is indeed a straight line on the plane.